Hi, in this video, I'm going to discuss the physical significance of wave function in quantum mechanics. We all know that in quantum mechanics, wave function is one of the very important parameters in evaluating or calculating different physical properties of a system. Though it is a mathematical function and as such, it does not in itself gives much about a system, one can obtain a lot of measurable quantities out of the wave function. So the knowledge of the wave function is very important in quantum mechanics in the study of the system. I'll proceed on to discuss some very fundamental ideas about the wave function. First, the wave function is a purely mathematical function. The essential idea of representing a quantum object such as an electron or a proton or any other particle, microscopic particle, arises from the de Broglie hypothesis. The de Broglie hypothesis tells us that it is possible to associate a wave of wavelength lambda to any moving object in quantum mechanics via the expression lambda is equal to h over p, where p happens to be the momentum of the object. Therefore, this can be written as lambda is equal to h over mv, where m is the mass of the quantum object and v is its velocity. Now, the moment we are able to associate a wave nature to the particle happens to have a duality in nature. So this is one of the fundamental ideas in quantum mechanics, that is wave-particle duality, which we owe to de Broglie. The moment we associate a wave with a particle, and wavelength we can calculate based on the momentum value of the particle, it is interesting that a wave function can be associated to such particle. So, as such, the wave function is a mathematical quantity. We represent the wave function associated with any quantum object using the notation psi of x. This is for a one-dimensional function. As such, in three-dimensional space, our reality exists. So, we have a wave function x, y, z and t. So, the wave function is a mathematical function which is function of at least 4 variables, 3 spatial which are x, y and z, and 1 temporal which is t. So 3 space variables and 1 time variables are the independent parameters which when varies, the wave function will vary accordingly. So mathematically if you see, this is a function of 4 variables. So in a 3-dimensional space, therefore, our wave function is a function of 3 space variables and of course 1 time variable. Right. Now, what is the physical significance of the wave function? What we are going to get out of this wave function? As such, the wave function does not give much information because it just is a mathematical function which tells us that how the wave amplitude varies in space. The wave amplitude associated with a wave, which is in turn representing a particle, does not as such give much physical information. But the moment we do modulo square of this wave function psi, what we are getting is very interesting, physically measurable quantity called probability density at a given point in space at a time t. So it is probability density, which is nothing but modulo psi squared. Now as such, therefore, psi can be considered to be nothing but probability amplitude. So the larger the value of psi at a particular point in space, at a particular time, the more is the probability of finding the particle at that point. So this is the probability interpretation of the wave function. So psi as such can be thought of as a probability amplitude, and the moment I do modulo square of it, I get probability density, which is a real measurable quantity which has a physical meaning. Now this being a density, if I integrate it over entire space or over entire volume, I should get probability. So the integral over entire space extending from minus infinity to plus infinity of this quantity, which is modulo psi square, which we call probability density, over the entire volume dV, should always give me 1. This condition in quantum mechanics is called as the normalization condition. Any wave function that satisfies this condition, that is the normalization condition, is eligible to represent a quantum object. So that is a valid wave function. So though wave function is a mathematical quantity, it gets physical meaning the moment it satisfies this normalization condition. One of the very important aspects of a wave function, one of the important qualifications of a wave function is it should be normalizable mathematically. Then it has a physical meaning, it acquires a physical meaning. Right. Now, what are the different properties of this wave function? We should briefly try to discuss those properties. Well, as such, the wave function is a complex function. So it is a complex function. The moment we say it is a complex function, it has real and imaginary parts. The wave function should be continuous function. It is a continuous mathematical function. So any discontinuous function cannot be therefore a wave function in quantum mechanics. So it should be a continuous function. The wave function should be differentiable at all points in space. That is, the first derivative at least should be differentiable with respect to, of course, x, y, or z. The wave function should be differentiable. That means these quantities should exist. They should not be equal to 0. Not only the wave function is continuous, even the differentials of the wave function with respect to the spatial coordinates are also non-zero. So even the differentials are continuous and non-zero. These are some of the mathematical aspects of a wave function. Yes, any function that is normalizable is also a wave function. So it should be a normalizable function to be called as a wave function. Right. These are some of the interesting properties, and the moment we know the wave function, we will be able to calculate a lot of measurable quantities, physical quantities out of this wave function. So the particle's position, the state of the particle to be whole, the particle's position, momentum, energy, angular momentum or spin, all these parameters can be calculated from the wave function if you know the wave function, because the wave function as such represents the physical state of a system, quantum system, physical state of a quantum system. For example, an electron. The wave function can represent an electron in a particular state. So an electron in a quantum state can be represented by a wave function, appropriate wave function, let us say. Now, the probability amplitude and the probability density, for example, for an electron in an atom, one can calculate the orbital shapes. So the orbitals, for example, that we study, different shapes, s orbital, p orbital, all this can be obtained from the probability density calculated for a given wave function representing the electron in that particular quantum state. So the quantum state for an electron in an atom, for example, can be n is equal to 1. The principal quantum number can be n is equal to 1. Now we know that the other quantum numbers start arising from this quantum number. So n is equal to 1 is the principal quantum number. The other possible states such as the orbital quantum number, the azimuthal quantum number, and the spin quantum number, all the other quantum numbers will together contribute to the definition of the quantum state of that particular electron in the atom. So the orbital shapes and all arise out of calculation of that probability density. So if we say that there is the electron is in the s orbital, that means around the nucleus there is a spherically symmetric region which is forming the s orbital, within which the electron can be present anywhere. Therefore, in quantum mechanics, to precisely say that electron is in this particular position is not allowed. That is because of Heisenberg's uncertainty principle. Please do look out for another video of mine in this channel on Heisenberg's uncertainty principle, where I have discussed the Heisenberg's uncertainty principle in more detail. So because of the prevention of locating the electron with infinite precision around the nucleus in an atom, the electron acquires what is called a fuzziness. This fuzziness leads to occupation of the electron in a region in space around the nucleus. Therefore, we don't no longer in quantum mechanics talk about electron orbits, specified orbits, but we talk about regions around the nucleus called as orbitals having special shapes. S orbital is spherically symmetric. We know that p orbital has dumbbell shapes, and d and f and so on and so forth. So these are some of the very interesting physical aspects of a wave function. Another very important property of the wave function is what is called orthogonality. Now, to conclude, let us begin to discuss the orthogonality property of a wave function in more detail. Right. Let us now discuss the orthogonality of the wave function in some detail. One of the important properties of the wave function is orthogonality property. What is orthogonality property? Now, we know that in three-dimensional space in which we all live in, it is possible to represent any vector arbitrarily in terms of three mutually perpendicular vectors along the three directions in space, that is x direction, y direction and z direction. So the unit vectors along these three directions can be called as x cap, y cap and z cap. Now this vector v in space, in three-dimensional space, therefore can be represented in terms of these three orthogonal vectors. So we can have Vx of x cap plus Vy of y cap plus Vz z cap. Now these three vectors are called unit vectors or unit basis vectors. So any vector in this three-dimensional space then therefore can be represented in terms of these three vectors, these three unit basis vectors. So in three dimensions, it is not possible to have any other vector which is not mutually perpendicular to these vectors. So these three vectors forms a complete set of vectors, basis vectors. Complete set of basis vectors, and we don't need any other vectors to represent in arbitrarily any other vectors. So complete set of basis vectors are three. So in three dimensions, we need only three vectors which are independent of each other to represent any vectors. So these Vx, Vy and Vz are called components of the vector, arbitrary vector that we decide to represent in the space. Components, vector components. Right, this is the case in three dimensions. Whereas our wave function in quantum mechanics is a complex wave function. So this wave function is actually represented in what is called infinite space, or space with infinite dimensions, infinite dimensional space. So our vector is a complex function, our wave function is a complex function rather, and it is a vector in infinite dimensional space. If that is the case, then we should be able to represent this as a vector in infinite dimensional space. Let us call the basis set like this x, y and z cap in the three-dimensional space. Let us call that basis set as phi of, let us say, n, because this is infinitesimal, means let us say n-dimensional space, nd space. In this n-dimensional space, we have n basis vectors, n basis vectors, complete set. That forms the complete set of vectors that are sufficient to represent any vector, arbitrary vector in this n-dimensional space. So our psi is a vector in such a space. Therefore, the psi can be therefore represented in terms of phi vectors. Phi is the basis set. So if I have to write therefore the complex wave function psi in such a space, then I'll be using some components, arbitrary components, let us say Cn phi n, summation of n going from 1 to n is equal to, let us say, some m, or m going from 1 to m is equal to n. The index is m here and the space is n dimensional. So index is m. N is the space. So mathematically, if you want to understand this, this is how we have to represent this. Cn are the components of the vector, or components of psi. What are these components physically? These different components of the wave function in an n-dimensional space is nothing but different states of the system, different possible states of the system at a time t. So what we are representing here is psi at a time t. So at the same time, it is possible for the system to exist in different quantum states, and that is represented by this. Now, just like how in the normal three-dimensional space we can take a dot product of one vector with other vector, here also we can take dot product of two wave functions in n-dimensional space. Then we have the notation of, let us say, psi phi. This is called the bracket notation, Dirac's bracket notation. I will have to post another video on this notation separately. Please do look out for that video as well. Bracket notation. So the bracket notation in n-dimensional space are the inner product or dot product. This is called dot product or inner product. It's similar to the dot product that we take, also called as scalar product. So we are trying to take the dot product of these two functions in n-dimensional space. By doing this, what we are doing in real space, if at all we have two vectors, let us say u and, let us say u vector and v vector. Then we will have dot product as ux vx plus uy vy plus uz vz. These are the components that are multiplied and we obtain the dot product. In the n-dimensional space, in the bracket notation, this happens to be what is called inner product or scalar product. That means different possible eigenvalues are accessed. That means different possible states of this quantum system at a given time t are being accessed by doing this bracket inner product operation. So the system has a simultaneous option of existing in any of the accessible quantum states, and by taking this inner product we are trying to get that particular eigenvalue in which the system is presently existing. That is what we do by taking this inner product or scalar product. Now when we say orthogonality, therefore, if two vectors are said to be orthogonal, they are perpendicular to each other, and if the dot product is 0, then they are called orthogonal vectors. So if in this present case in 3 dimensions, if u and v are orthogonal vectors, then the dot product is 0. Okay, so for orthogonality, the condition therefore in quantum mechanics is a wave function, let us say, is said to be orthogonal if two functions, let us say psi and phi, are said to be orthogonal if a complex conjugate of the first function multiplied by the second wave function over entire space leads to 0. Then these functions psi and phi are said to be orthogonal. Orthogonal functions. That is the projection of a state onto itself. That is what this means in quantum mechanics. Right. So by orthogonality, therefore, what we mean is if these two functions are orthogonal, then the integral is going to go to 0. Right. What we actually therefore mean is psi is a vector in n-dimensional space or in an infinite dimensional space. Right. So by doing this operation, we are taking the inner product or the scalar product, or in vector analogy the dot product of this wave function psi with the basis set phi in that space, because phi is the set of basis vectors for that infinite dimensional space. So what we are doing is here we are representing that as dx psi star phi. If this is equal to 0, then the two wave functions are orthogonal, and if it is not equal to 0, this is going to give us the component of the vector psi, component of the vector psi, let us say some component cm, some arbitrary component. That means this value points to the value of the wave function in that space. Therefore psi can be represented as, because psi is a function of x is a continuously varying variable. Continuously varying variable or parameter. That means in this space we cannot have individual basis set which are non-continuous. We have continuously varying basis set. So phi is having infinite number of vectors. Phi is a basis set with infinite number of vectors, and we call it n-dimensional because it's infinite. We can even call it n-dimensional. In that space, if you want to represent the psi in terms of phi, then we'll have infinite number of components. To access any one particular component or one value at a point x for psi, we have to do this operation. We get the value of psi at a particular point. So this is the importance of orthogonality of the wave function. Thank you.